Hi, my name is Daniel Green, and today we're going to do a circuits problem using mesh analysis. So the first thing that you want to do with one of these types of problems is identify all of the current loops. So I'm going to do that now. So over here, we have like current loop I1. Over here, say we have current loop I2. And over here, current loop I3. Now for the next part of the problem, I'm going to have Brett come up here and do the next part.
Alright, so getting back to the fundamental basics of mesh analysis. Mesh analysis is derived from something called Kirchhoff's voltage law, or KVL for short. And basically what that annotates is the fact that the voltage in any given loop from up to down in a circuit will have a net voltage of 0. So the same amount of voltage going up in a particular loop has to be the same going back down. Just opposite direction, negative sign, all equates to 0. It's pretty great. It's wonderful stuff. And that can be given, again, for any single loop in the entire circuit. So Dan wonderfully supplied us with the designations of every loop in the circuit. Basically what a SuperMesh is something that you need to implement whenever you have a current source or a dependent or independent current source. And we have both, so that's cool. So what you're going to want to do when implementing a SuperMesh when you have these current sources is you're going to want to ignore the individual current sources, pretend they weren't there for a moment. And once you do that, you can figure out pretty quickly that you need to imagine as if they weren't there, and then imagine what you would do when identifying the loops once these sources were removed. So if these sources were to be removed, the whole circuit would just be this one rectangle. 3 resistors, 2 voltage sources. This one is 40 volts, and you would do that. So here is your SuperMesh. So anyways, you have this super mesh, which basically is taking the net current going from the upper left all the way right back down. Now, you're going to want to start by writing the equation for that SuperMesh loop. And how you do that is taking each of the individual components attached to that loop. So we're going to start by taking this 100 volt source. And this loop does go clockwise and enters the negative terminal of the voltage source. So we can denote that as negative 100 when starting our equation. And then the next component would be that 4 kilo ohm resistor. And Kirchhoff's voltage law is all about current. And it's all about voltage. So, more voltage than current. So, basically, when writing out these equations, you're going to keep in mind Ohm's law of V equals IR. And you're basically, in KVL, summing up all the voltages going up and back down in the circuit. So, you have negative 100 volts coming here, and then you have a 4 kilo ohm resistor. Now, you're still going to want to keep in mind this I1, I2, and I3, which exists in the actuality of the circuit. So, that I1 is being attached to the 4 kilo ohm resistor. So we're going to denote that as I1. And that, IR, voltage, that's also voltage. So you're basically summing up the voltages in the entire thing and then setting the entire equation equal to 0 because it's all supposed to net a 0 volt. So, you have that 8 kilo ohm. So you have 8K times I2. I don't know why I'm using so many parentheses, but I want to anyway, so it's going to happen. Then you have that 2 kilo ohm. You're using I3. And then you have the loop ending at that 40 volt voltage supply entering the positive terminal, so we denote that as 40 volts. Like I said, you set the whole equation equal to 0 because it's supposed to net 0. Now, once you do the SuperMesh, you're going to want to pay attention, again, to reinstating these two current sources and then saying, okay, we're back with I1, I2, and I3. So we need to take into consideration these two current sources somehow. And the way we do that is by finding the equation for these individual current sources, which will give us a system of equations that we can then solve, finding the current at these individual loops. And once you find the current for these individual loops, you can basically take the pattern of the loops to determine the current anywhere in the circuit, except through components, obviously, just like at any node. So we start by taking this 4 milliamp source here. What we notice is when you represented it with the variables I1, I2, and I3, or 3 loops, that I2 goes in the same direction as that current source, but I1 opposes it. So, using simple logic, we say that 4 milliamp source is equal to I2 minus I1. Simple, right? Then you can simplify that as I1 plus 4 milliamps equals I2. Oh, I'm going to make that lowercase so keep it consistent. There we go. And now we're going to take, the only difference between this independent source and that dependent source is that instead of writing, whatever constant it's equal to, you keep that variable. So, for example, you have I2 going the same direction as this dependent source and I3 opposing it, so using simple logic skills, we can do 2I1 is equal to I2 minus I3. And you can simplify that down to 2 equal to 2I1. I don't know, I'm kind of in the way here. Plus I3. And that'll help when you're solving the system of equations. Now you're left with the system of equations, and the person who will be taking over that now is Morgan.
So, get out of here.
Oh, great. Oh!
That's not the name.
Answers you should get are I1 is equal to 2 milliamps, I2 is equal to 6 milliamps, and I3 is equal to 2 milliamps. So you can take I2, plug in the first equation. After you plug this in, you take this entire equation and plug it into here so that you can have everything all in terms of I1. And once you get I1, you can take I1 to get I2 in this equation. And now that you have I2 and I1, you can use those to get I3. And doing that, you should get these answers. And remember you can ignore the kiloohms and the milliamps because they turn out to be all milliamps. That's how it works.